Section 3.3, Trigonometric Substitution. Now this is again from OpenStax Calculus Volume 2. So if you want this information, if you want the textbook form of this, you can always go to, wherever it is, the web address at the bottom of the page. So feel free to download all of this for free from there. Alright, so our problems at this point are going to involve a lot of square roots. Okay. Now there's a reason that we're going to do this, but if we have an integral involving the square root of a squared minus x squared, okay, we are going to do one particular substitution, and that is x equals a sine theta. Okay, so in this case, the a value is 3. It's 3 squared. So we're going to use a substitution on this and turn this into, well, if x is 3 sine theta, then dx is 3 cosine theta. So we'll substitute this as the integral of the square root of 9 minus x squared. That would be 9 sine squared theta. And our dx is going to become times 3 cosine theta. And there should be a d theta there. Well, I can factor a 9 out of that. And actually that comes out of the square root as a 3. 3 square root of 1 minus sine squared theta times 3 cosine theta d theta. Now, based on our Pythagorean identity, sine squared plus cosine squared equals 1, this becomes 3 cosine theta times 3 cosine theta d theta, or simply put, 9 cosine squared theta d theta. Now you should notice at this point this integral could be evaluated based on that previous section, trigonometric integrals. Okay. In general though, we are going to convert something with a square root into something with cosines and sines, tangents, secants, and that actually makes our integrals calculatable. Okay, we can make them integrable that way. So here is our general policy using this reference triangle. Now the reason before I get there is that if sine theta equals x over a, if it equals x over a, then that is the opposite. Let's go back, make that. Okay, that is our opposite over our hypotenuse. And so if you determined what the third side is here, that would be the square root of a squared minus x squared. Therefore, anything with a square root of a squared minus x squared, we're going to use a substitution of sine. Alright, so here is our general policy, our problem-solving strategy. Okay, so first we want to make sure it can't be evaluated some other way, some easier way. But if we have something with a square root of a squared minus x squared, okay, and you see the 3 examples there, they can all be done with u substitution, but some of them don't work like that. So if it doesn't work with u substitution or a simple formula, then we're going to make the substitution of x equals a sine theta, which then makes dx a cosine theta d theta. Right. And then we're going to work this around until we actually get an a cosine theta, is what always ends up happening there. Simplify it, evaluate it based on how we did trigonometric integrals previously, and then we'll use a reference triangle at the end to turn it back into terms of x. Okay, so let's go ahead with this one. Now we already showed, first we said x is 3 sine theta, which makes dx 3 cosine theta d theta. Now based on this problem solving strategy, we're going to replace this. 9 minus 9 sine squared theta times dx, so that is 3 cosine theta d theta. And this becomes the integral of 3 cosine squared theta. Or actually, I'll go ahead and combine both of those. I was going to say times 3. That becomes a 9 cosine squared theta d theta. Alright, now we can use our half angle or double angle identities with this. Okay. So that cosine squared becomes 1 plus, so 9 1/2 plus 1/2 cosine 2 theta. Okay, and so when we take the integral of that, That is just a simple substitution. We get 9 over 2 theta plus 9 over 4 sine theta, because of that factor of 2 in there. Plus c. Alright. So, next we need to take a glance at turning this back into terms of x. Okay. So, based on our x equals 3 sine theta, that is sine theta equals x over 3. So that means our hypotenuse is 3, our opposite is a, which makes this side over here the square root of 9 minus x squared. Okay, and of course, theta, our angle, is there. All right. So sine, okay, sine theta is opposite over hypotenuse. So sine is actually x over 3. Actually, back up just a second, because that is a 2 theta there. So this actually becomes 2 sine theta times cosine theta plus c. Can't forget about that. So this will be 9 over 2 theta plus 9 over 2 sine theta cosine theta plus c. Okay, so now going back for our substitutions. Sine theta is x over 3. Cosine theta is the adjacent over the hypotenuse, so that is the square root of 9 minus x squared over 3. And theta itself is the arc sine of x over 3. Right, so putting this back in terms of x, I have 9 over 2 arc sine of x over 3 plus 9 over 2 times x over 3 times the square root of 9 minus x squared over all over 3 plus c. Now, of course, we can make that look a little bit nicer by multiplying the denominators there. Let's go ahead and do that. Make that all, so it'll be 9x over 18, so 1/2. That all over 1/2. 1/2 x, yes. So make that plus 1/2 x. There we are. Alright, so as you can see, the process is convert it into sines and cosines, apply some of the methods we had previously, convert back to x's. Alright, so number 35, square root of 4 minus x squared over x. Okay, it's still in the same form, so I'm going to make x equal, make sure that doesn't blend in there, make x equal 2 sine theta, which then makes dx equal 2 cosine theta, d theta. Substitute that in. Okay, so this will be the square root of 4 minus 4 sine squared theta over 2 sine theta. And then we have our d theta in there. Alright, oh, d theta though, or dx, we need to replace as times 2 cosine theta. D theta. Alright, that is a complete substitution there. Alright, so this becomes, we factor out a 2, and that is going to become a 2 cosine squared theta over 2 sine theta times 2 cosine theta d theta. And this is a square root right there. I need to leave that in there. Okay, so that'll just be a cosine. So this should all become the integral of 2, and then we have a cosine squared over sine d theta. Alright, my next move would then be to possibly convert the cosines into sines, so using our Pythagorean identity. So I'll just factor my 2 out there. 1 minus sine squared theta over sine theta d theta, which is the integral, 2 times the integral of cosecant theta minus sine theta d theta, which is 2 times integral of cosecant is the natural log absolute value of cosecant theta, keeping that variable in there, cosecant theta minus cotangent theta minus, and we'll have 2 cosine, and it'll be a positive cosine there, cosine theta plus c. Okay, the one thing we have left to do is convert this back in terms of x's. Okay, so draw my triangle. Right, there's theta. Right, so sine is the opposite over hypotenuse, so this is x over 2. So this is the square root of 4 minus x squared. Alright, so my cosecant is 1 over sine. Cosecant's 1 over sine, so that is 2 over x. Alright, cotangent, or actually let's do cosine next. We will need that. Cosine is adjacent over hypotenuse, so that is the square root of 4 minus x squared over 2. Cotangent, we need that. Cotangent is going to be tangent is opposite over adjacent, so this is adjacent over opposite, so this is the square root of 4 minus x squared over x. So replacing this, we get 2 natural log absolute value of 2 over x minus cotangent square root of 4 minus x squared over x, absolute value, plus 2 times cosine, so that is 2 times the square root of 4 minus x squared over 2. The over 2, the 2's will cancel, so that is plus the square root of 4 minus x squared plus c. And there we have our integral, our antiderivative in terms of x. Be familiar with some of your trig, obviously. Alright, let's move on to number 36. Okay, now this one's a little different, but it's still in that same form, square root of a squared minus x squared. So I will still make a substitution of x equals 1 times sine theta. Wish I could complete one of my thetas for once. Alright, and dx equals cosine theta d theta. So this is going to be the integral of, I can go ahead and replace the x cubed, is going to be sine cubed theta, square root of 1 minus sine squared theta, and then dx, we need a cosine there, cosine theta d theta. Okay, now this portion right here is going to be a cosine squared, which the square root of that's just cosine. So this is going to be the integral of sine cubed theta times cosine squared theta d theta. Okay, I'm going to go ahead and take one of those, or 2 of those sines, and convert that into cosines. So this is the integral of 1 minus cosine squared theta, cosine squared theta, and then there's one more sine Okay, so hopefully you can see what I did there. I took a sine squared over here and brought 1 down there. All right, now if I make u, I'm going to do a u substitution now. If I make u cosine, because I have a single sine hanging out there, u is cosine, du is negative sine theta, d theta, so negative du sine theta d theta. This is going to be negative integral of 1 minus u squared times u squared times du. Okay, well, that will be, once I distribute that, of course, that will be a u to the 4th, or minus u to the 4th, which I'll go ahead and factor that in. That's going to be a positive u to the 4th. Okay, and then we have a minus u squared du. So u to the 5th over 5 minus u cubed over 3 plus c is my integral. Now, converting that back into sines and cosines, and eventually back into x's, that'll be 1/5 cosine theta to the 5th minus cosine cubed theta over 3. I guess I could have done 1/3 there. I did there. Plus c. Alright, now for our thetas. We need to back this up into x's. Alright, so cosine theta, so using my triangle, okay, if sine is x over 1, my cosine is the square root of 1 minus x squared over 1. So each of my cosines becomes a square root of 1 minus x squared. So this will be 1/5 the square root. Actually, I'm going to go ahead and make this, because I'm going to raise it to the 5th power, I'm going to go ahead and say 1 minus x squared to the 5 over 2. Okay, the square root, and then I'm raising it to the 5th power. Minus 1/3 1 minus x squared to the 3 over 2 plus c. And I would suggest looking at these repeatedly, because some of these things just don't sink in with the first time you see it. Okay, so make sure you have a habit of going back and listening to some of the explanation and the steps as you go. Again. Okay, let's look at number 37. This one we are not going to evaluate. We are going to replace this in terms of sine. Okay, so first notice that we have a squared minus x squared. So we'll go ahead and make a substitution of a equals sine theta, and dx is cosine theta d theta. Alright, so the x cubed is going to be a sine cubed theta, and this is going to be 25, oh, there should be a 5 in there, 5 sine theta, so 5 cosine theta. So that'll be 125 when we cube that. Now, the square root of 25 minus 25 sine squared theta. Now our dx is going to become 5 cosine theta d theta. Okay, well, that 25 sine squared is going to become a 5 cosine theta. 125 sine cubed theta times 5 cosine theta d theta. Alright, then those cancel out, and this is the integral of 125 sine cubed theta d theta. Okay. Now this says do not evaluate, so this problem is complete. However, you'd likely want to take the sine squared in there and turn that into a cosine, 1 minus cosine squared, and use a u substitution there. For now, that is it. Alright, let's look at number 38. Well, before we get there, actually, we have a second type of integral, the square root of a squared plus x squared. Okay, so the big difference here is that if we have a plus a squared plus x squared, we're going to use the substitution of x equals a tangent theta. And this again has to do with our reference triangles. And then dx being a secant squared theta. And this actually will yield an a secant theta. Okay, so here is the reference triangle for that. Tangent, okay, if we use that substitution, then that's x over a, opposite over adjacent, and then our third side is the square root of a squared plus x squared, which is what we're trying to work with our integral, our integrand. So let's keep that in mind, and then we'll move along. So write down what you need to. Alright, so 1 plus x squared, the square root of that. So this is going to be, a is 1. Okay, so I'm going to go ahead and draw my triangle and my substitution. Alright, so first we have got x equals tangent theta, because a is 1. X is tangent theta, so dx equals secant squared theta d theta. So over on our triangle, that is x, so opposite is x, and our adjacent is 1, and the square root here is 1 plus x squared. Okay. Let's go ahead and take that as dx. Dx is going to be d theta, so we'll have a secant squared theta d theta over the square root of 1 plus tangent squared theta. Alright, well, 1 plus tangent, okay, is the same thing as secant squared. So this becomes the integral of secant squared theta d theta divided by secant theta, which is just the integral of secant theta. All right, that leads us to say this is going to be the natural log of the absolute value of secant theta plus tangent theta plus c. Now we cannot leave it that way. So secant is 1 over cosine. Okay, so that would be hypotenuse over adjacent. So that is the square root of 1 plus x squared over adjacent, which is 1. And our tangent is the opposite over adjacent. So that was x. Well, we actually made the substitution earlier. X is tan theta. So this is the natural log of the absolute value of the square root of 1 plus x squared plus x plus c. And there we have it. Next, we're going to have an application of this for 39. Find the length of the curve y equals x squared over the interval 0 to 1/2. Okay, so first off, arc length. Go ahead and write that up here. Arc length is the integral from 0 to 1/2 of the square root of 1 plus f prime of x squared. So f prime here is going to be 2x. So square that, we have 4x squared dx. Now this is of the form a squared plus x squared. Okay? It's of the form a squared plus x squared. Okay, so in this case, we'll go ahead and draw our triangle. Okay, we'll go ahead and say secant, or, yeah. No, I believe we said tangent actually. So we'll make this tangent. Theta equals 2x, because that is what is being squared there. Okay. Okay, so once we make that substitution, tan theta is 2x. Well, one thing to notice is that actually means x equals, okay, so that implies that x equals 1/2 tangent theta, and dx is 1/2 secant squared theta d theta. Alright, so let's go ahead and make these substitutions. That is going to be, I'll come back to this reference triangle in a second. That integral becomes the integral from, now let's go ahead and make the change of variable. If we plug 0 in for theta, or if we plug 0 in for x and solve for theta, this ends up being 0 to pi over 4. Okay, the square root of 1 plus 4x squared, so that's 4, and then we'll have 1/4. So actually this ends up being just tangent squared theta. And then our dx becomes 1/2 secant squared theta d theta. Okay, the square root of 1 plus tangent is going to be just a secant. So this is the integral from 0 to pi over 4. And that's a secant times a secant squared. So this is going to be 1/2 secant cubed theta d theta, which we know what secant cubed is. Integral of that is, keep the 1/2 factor, that's the natural log of the absolute value of secant theta plus tangent theta plus 1/2, oh, there's another 1/2 in here, plus 1/2 secant theta, tan theta. Okay. And this is all going to be evaluated. This will be 1/4 natural log absolute value of secant theta tan theta plus 1/4 secant theta tangent theta. Now this is evaluated from 0 to pi over 4, our change of variable, which is exactly 1/4 times square root of 2 plus natural log of square root of 2 plus 1 that's exactly what that is, but that is approximately 0.5739. There's the length of that curve. Now, previously we would have gotten to the integral stage of this, and then just simply used cocalc. But in this chapter we want to show all of our work, all the steps where things are coming from. And that is important in this. Alright, number 40. Rewrite this using tangent as a substitution and don't evaluate. This is kind of like that last one we did with sine. Okay, and actually we want to use tangent, or 2 tangent theta for that because our a value is 4. So this is going to be x cubed, so that would be 8 tangent cubed theta, square root of 4 tangent squared theta plus 4, which will become a 2. Okay, I'll leave this part here. This will become a 2 tangent theta plus 1, so that'll be a secant. Alright. Okay. And we need our d theta actually. So we should have had a d theta, or dx becomes 2 secant squared theta. So 2 secant squared theta d theta. Alright, so then we've got another secant squared, which will become a secant cubed. So we have the integral of, that will be 32. 32, we have a tangent cubed theta, and then we have a secant cubed theta. D theta. Alright, the last kind of substitution we have is if we have the square root of x squared minus a squared. This is very similar to the first one we had. Just a switch in there. The big difference there is if it is a square root of x squared minus a squared, then what we are going to do is make a substitution of a secant theta, and then dx will be a secant theta tangent theta d theta. Okay. Now, a thing to point out here is that we actually have something different depending on the value of a. Okay. If a is greater than or equal to a, or if x is greater than or equal to a, then we get a tangent theta as the answer to our square root when that simplifies because of the absolute values. If x is less than or equal to negative a, then we actually get negative a tan theta. Okay. I believe both of our examples are going to have a positive tan, but that is worth noting. Okay, so be careful about the domain that we are looking at. So these are going to be given. And there are two example reference triangles based on the absolute value. There are two versions of that. Okay. So find the area between the graph of f of x equals x squared minus 9 and the x-axis over 3, 5. Okay. So first, the a value is 3. We are always going to be greater than that, so we are going to use the positive version of that. We will be using this one right here. All right, so we will make our substitution. X equals a secant theta, which makes dx secant theta tangent theta d theta. Now, we are finding the area, so this really turns into this. We have the area is the integral from 3 to 5, the square root of x squared minus 9 dx, because we're between the x-axis. Okay, now we are going to have to change our variables here. Okay, change the endpoints. But from 3 to 5 to, well, let's see. If x was 3, that would be arc secant of 1. Okay, which I believe is 0. Yes. Alright, so that is going to be, in the end, from 0 to the arc secant of 5/3. Okay, those are going to be our change of variable there. Alright, now the square root of x squared, so that is 9 secant squared theta minus 9 d theta. No, dx is going to have times 3 secant theta tangent theta d theta. Bring that over here. That is going to be the integral from 0 to the arc secant of 5/3 of 3 and then that is going to become a tangent. So 3 tangent theta times 3 secant theta tangent theta d theta. Okay, so that's the integral from 0 to secant inverse 5/3 of 9 tangent squared theta secant theta d theta. And it would be a wise choice to probably convert that tangent into secants. So that will be secant squared minus 1. So 9. So the integral, that's going to be 9 times secant squared minus 1 secant 0 to secant inverse of 5/3. Okay, that'll be a secant cubed in there. Okay, so bringing that up here. Integral from 0 to inverse secant 5/3. Okay, that'll be a 9 secant cubed minus 9 secant theta d theta. Alright. Now, secant cubed, we know, is 1/2 plus all of that. So that is 1/2 natural log, and I'm going to go ahead and bring the 9 in there as well, so that's 9 over 2, natural log of secant theta plus tangent theta, okay, plus 9 over 2 secant theta tangent theta, minus, we still have our 9 secant theta. Well, the secant is just the natural log of the absolute value of secant theta plus tangent theta. Now, we are evaluating this from 0 to pi, no, to inverse secant. That's what we have on this one. We don't have an exact value. Secant inverse of 5/3. And that is 10 minus, I'm just cut to the chase, 10 minus 9 over 2 natural log 3. I didn't actually get an approximate value for that, but that is the exact value. 10 minus 9 over 2 natural log of 3. Okay, the last one we have in this, dx over the square root of x squared minus 4, and notice that x is greater than 2. Okay, our a value is 2, so we are still going to use the positive version of that square root when we get there. Alright, now we will make our substitution of x equals 2 secant theta dx equals 2 secant theta tangent theta d theta. So our substitution here is for dx 2 secant theta tangent theta divided by d theta divided by the square root of, squaring that is 4 secant squared minus 4, which will become a tangent. So that will be the integral of 2 secant theta tangent theta d theta over 2 tangent theta. Okay, well, that will be just a secant, or yeah, just a secant. Integral of secant theta d theta, which is going to be natural log, absolute value of secant theta plus tangent, we need an absolute value there, plus c. Now, we need to determine, based on a triangle, what these are going to become. So, secant is 1 over cosine, so this is hypotenuse over adjacent. So, hypotenuse over adjacent, so this is the square root of 4 minus x squared. So, secant, well, secant is x over 2. So the absolute value of that plus, now tangent is opposite over adjacent, so this is the square root of x, or 4 minus x squared, x squared over 2, absolute value plus c. Okay, and that, adjusting that, that is the end of that question. Okay, and that is the last question in this section, so 3.3. So make sure you can do your homework, and if you have questions about this in class, please feel free to ask. That's what this is for. That's it.